Artificial intelligence (AI) has emerged as one of the most transformative forces in modern science, fundamentally altering the way research is conducted across virtually every discipline, from physics and chemistry to biology, medicine, and engineering, and its impact continues to grow at an unprecedented pace. At its core, AI refers to the development of computational systems that can perform tasks traditionally requiring human intelligence, including pattern recognition, learning from data, decision-making, and problem-solving. And when applied to scientific research, AI brings an entirely new dimension to both the speed and scope of discovery. One of the most significant ways AI is shaping research is through its ability to process and analyze enormous datasets far beyond the capacity of human researchers, enabling the extraction of insights that would otherwise remain hidden. In fields such as genomics, for example, AI algorithms can quickly sift through millions of genetic sequences to identify correlations between genes and diseases, paving the way for the development of personalized medicine and targeted therapies. While in climate science, AI models can integrate complex variables from atmospheric, oceanic, and terrestrial data to make accurate predictions about climate change patterns and extreme weather events. Beyond data analysis, AI is also revolutionizing experimentation itself, particularly in areas that involve high throughput or repetitive processes. Robotic systems guided by AI can conduct experiments in laboratories autonomously, testing thousands of chemical compounds for pharmaceutical development or simulating physical experiments under a variety of conditions to identify optimal outcomes, thereby drastically reducing the time and cost traditionally associated with experimental research. This automation not only accelerates discovery, but also reduces human error, improves reproducibility, and allows researchers to focus on creative and conceptual aspects of science rather than routine tasks. Furthermore, AI's predictive capabilities are enabling researchers to model complex phenomena before conducting actual experiments, as seen in materials science, where machine learning algorithms predict the properties of novel compounds, or in astrophysics, where AI assists in simulating cosmic events, providing insights that guide observational strategies. One of the most fascinating aspects of AI in scientific research is its ability to generate hypotheses and propose experiments in ways that can surpass conventional human intuition. Generative models, a branch of AI, can suggest potential molecular structures, protein folding configurations, or chemical reactions that researchers may not have conceived, effectively expanding the creative boundaries of science itself. This capability has been exemplified in the development of new drugs and vaccines, where AI-driven platforms were instrumental in predicting protein structures and interactions critical for combating emerging diseases, dramatically reducing the timeline from conceptualization to clinical trials. AI also enhances collaboration in science by serving as a bridge between interdisciplinary domains, integrating knowledge from biology, chemistry, physics, engineering, and computer science to provide holistic solutions to complex problems that cannot be addressed by a single field alone. The use of AI-driven simulations and virtual experiments allows scientists to test scenarios that are impractical, costly, or even impossible in the physical world, such as simulating the behavior of subatomic particles under extreme conditions, predicting the long-term ecological impact of environmental policies, or modeling the spread of pandemics under multiple intervention strategies. Beyond practical applications, AI is transforming the scientific process itself. From literature review to publication, natural language processing tools can analyze thousands of scientific papers, extract relevant findings, summarize trends, and even suggest new research directions, enabling researchers to stay abreast of the rapidly expanding body of knowledge and to identify gaps that warrant investigation. Moreover, AI facilitates reproducibility and transparency in research by meticulously documenting experiments, tracking data provenance, and providing tools to verify results, addressing long-standing challenges in scientific rigor. Ethical considerations also intersect with AI's role in research, as the technology raises questions about data privacy, bias in machine learning models, and the implications of autonomous decision-making in experimental design. Researchers are increasingly focused on developing explainable AI systems that provide not only predictions, but also understandable rationales, ensuring that human scientists can interpret and trust AI-driven results. The integration of AI into research workflows is also democratizing science. as cloud-based AI platforms allow institutions and researchers with limited resources to access powerful computational tools that were previously available only to well-funded labs, fostering global collaboration and accelerating innovation in developing countries. Furthermore, AI's impact extends to education and training in science, where intelligent tutoring systems and virtual labs provide personalized learning experiences, helping the next generation of scientists acquire skills in data analysis, computational modeling, and machine learning, which are essential for conducting modern research. In addition to its current applications, the potential future contributions of AI to science are even more profound. With advancements in quantum computing, neuromorphic processors, and autonomous laboratories, AI could eventually undertake complex problem-solving with a level of speed and sophistication that far exceeds human capability, enabling discoveries in areas that today remain largely theoretical, such as controlled nuclear fusion, deep space exploration, and the treatment of complex diseases like Alzheimer's. AI is also poised to play a central role in interdisciplinary fields such as systems biology, synthetic biology, and bioinformatics, where the integration of massive datasets and the simulation of intricate biological networks are crucial for understanding life at a fundamental level. While some skeptics argue that AI could supplant human scientists, the prevailing perspective is that AI functions best as an augmenting tool, enhancing human creativity, insight, and judgment rather than replacing it, by automating routine tasks, generating novel hypotheses, and providing analytical support that allows scientists to focus on interpretation, innovation, and the ethical dimensions of research. In conclusion, artificial intelligence is reshaping the landscape of scientific research in profound and multifaceted ways, accelerating the pace of discovery, expanding the boundaries of what is possible, enhancing collaboration and reproducibility, and democratizing access to advanced tools. By enabling researchers to process enormous datasets, simulate complex phenomena, conduct autonomous experiments, and generate innovative hypotheses, AI is not only making science faster and more efficient, but also opening entirely new avenues for understanding the natural world. Its influence permeates every stage of the scientific process, from conception to experimentation to publication. And while challenges remain regarding ethics, transparency, and human oversight, the transformative power of AI in science is undeniable, promising a future in which the integration of human ingenuity and machine intelligence leads to discoveries that were once unimaginable, fundamentally redefining our approach to knowledge and the very nature of research itself.